Swayam Prabha. Digital India. Educated India.
Now in continuation of proposed technique, given a solution space S and the operator P of x comma I such that S to S, which represent the transformation of the solution x in S, the transformation is parameterized by a variable I defined as some finite domain D, and the neighborhood nk of x of the solution x is the set of candidate solution P of x comma I, where x is a fixed and I takes any value from the domain nk of x equal to rho of x comma I belongs to S such that for all I in D. So, the function rho can be arbitrary function and return the solution y in S. Note that y can be incomplete solution. So, equation 3.8 can be violated for some indices. So, the proposed solver offers 10 different operations like insert, to optimization, move, swap and many more. So, the perturbation or randomized operators, they are intended to escape the local optimum by making a random, usually non-improving selection of the new solution x outside of the previously explored neighborhoods. There are 6 perturbations to choose from: double bridge, random reverse double bridge, reinsert, and random move, random swap and random move all. So, the construction strategies are functions that are used to generate an initial solution. There are 3 types of construction strategies implemented. One is a greedy, random and a random replicate. Random creates a random solution that satisfies the upper bounds and lower bounds. Random replicate generates one permutation of all the nodes and then depends the solution with the replicas of the permutation until lower bounds are satisfied. So, greedy constructs the solution iteratively, evaluating fitness after all possible node insertion and inserting the best node at every step. Therefore, the user defined fitness function must return a reasonable value even for incomplete solutions. So, the local search strategies are a function that are select the order in which the neighborhoods are explored. They perform the exploration until none of the operations are able to find an improving solution. So, the proposed solvers implements 5 variations of variable: neighborhood descent, the basic variable, basic variable neighborhood descent, pipe variable neighborhood descent, cycle variable neighborhood descent, random variable neighborhood descent and random pipe variable neighborhood descent. So, these are all the 5 variations. Finally, meta heuristic are most high level function that make use of all the other types of function to the optimizer. So, the proposed solver implement some established neighborhood orientation meta heuristic, namely iterative strength, iterative search ILS and basic variable neighborhood search. Additionally, an extension of BVNS called calibrated variable neighborhood search is proposed later in the talk. All these meta heuristic work on a similar basis. First, they generate an initial solution using one of the construction strategies. Then they iteratively call local search strategies, is search for the local optimum in the selected neighborhoods, that is minimizing the fitness using the operator function. After reaching a local optimum, the current solution is randomly altered by a perturbation function to escape the local optimum. So, the process is repeated until a timeout is reached. During the optimization, the generic optimizer collects metadata. This includes a histogram of improving operators, calls and a graph of the fitness with respect to the elapsed computation time. Steps in the graph are made after every improving local search call because there would be too many records if the graph included all the operator as well. So, user can define which components the optimizers invokes the JSON configuration file. There are also other parameters that the user should configure, like the number of threads in which the optimizer should run, or the maximum computation time, which is currently the only end condition for the optimization loop. Another important setting of optimizer decides whether the optimizer should accept the infeasible solution after every perturbation. If not, it would reset the solution to the state before perturbation and repeat the perturbation until feasible solution is acquired. Note that the perturbation or randomized selection function and the rest of the candidate solution they choose from is large. So, the probability of choosing an already explored solution is low. So, the problem specific component is a part that is implemented by the user. Nevertheless, this is not a tedious process. So, the amount of work is comparable for formulating the problem as ILP or CSP. So, the user has to implement a problem specific instance class. So, it has to initialize the mandatory properties of the abstract instance class like lower bound, upper bound vectors and a fitness function g of x. So, the user should also choose a suitable configuration for the given problem. The configuration can be tuned either in the trial error manner or by the specialized tuning tool like ERAS. So, the fitness function g of x should return the fitness of the solution x and its feasibility. So, the fitness function has to be designed efficiently both in terms of complexity and implementation, as it is the most frequently called function in the whole optimization process. So, the overall performance is heavily affected by the fitness function. So, user should also consider adding some kind of penalty p of x to the fitness function g of x. The purpose of penalty function is to add penalty to infeasible solution, so that the solution that are close to feasible solution are penalized less than solution that are further. So, all the problem specific components implemented for the purpose of this talk use the static penalty penalized. All the problem specific component implemented for the purpose of this talk use the static penalizing function. So, static penalizing computes penalty based only on the solution x, but there are also other type of penalizing like a dynamic, which usually increases over time, or adaptive, so which depends on the current solution quality. For more clarity, some of the frequently used terms in the section are explained. The elements A varies from 1 to n or the nodes A of the given problem. Solution x is a vector with a variable length m whose elements are the nodes from A. Solution substring is a vector x suffix substring equal to xi to xj, that is equivalent to some part of the original vector x to xm, where I and j varies from 1 to m and ith element of x is denoted xi. The frequency vector is denoted by f and corresponding to the original solution x, fa is a frequency of node A is a solution of x. Additionally, the lower bound and upper bound are the frequency of fa. Next, we are going to discuss the operator. So, this section describes all the implementation operators and provides their pseudo codes with an example. The following text: time complexity to find, insert, remove and reverse modification of the vector x are considered linear, that is order of m. And note the difference between the operators and modification. Modification is an atomic change performing on a vector x. Operators try out all possible modification and select the best one. Insert. Insert is an operator, is used mainly but not exclusively during the initial solution generation. It tries one node A in A to all possible location I in the solution x. After iterating through all possibilities, it returns the solution with the best fitness. If there was no improving modification, the algorithm returns the original solution. So, pseudocode is shown in the algorithm. On line 6 to 7, the function also checks that frequency Fa of the node A is not greater than or equal to upper bound. If that is the case, it does not try to insert node A. An example, insert operation where I equal to 2 and A equal to 4 illustrated the figure 3.6. The time complexity of the insert operator is order of cardinality of A m square, where modulus of A is a number of nodes and m is the length of x. Note that the length of the solution increases, so this operator cannot be used for problems with the upper bound equal to lower bound, with the exception of the initial solution construction. So, this is the code, pseudo code we are inserted, function insert x, and best x you have to fix, call it as x, and I varies from 0 to m, and new x you have to design for node A in A, f of A greater than or equal to nu into B A, continue, insert node A into x new at position I. Therefore, g of x new less than g of x best. Therefore, x best is x new and return that is x best. Therefore, this way we have to insert in between 1, 3, 2, 5, 6 and 4 is insert. So, we have the insert the operator where I equal to 2 and A equal to 4. So, remove is a counterpart of the insert operators. It tries to remove one of the nodes xi from all possible location I in the solution x. After trying out all possibilities, it returns the solution with the best fit. So, if no improving modification was made, the algorithm returns to the original solution. Therefore, the pseudo code is shown in the algorithm on line 6 to 7, and remove also skips the node A if the frequency Fa is less than or equal to LBA. So, an example, remove operation where I equal to 2 and A equal to 4 and illustrated the figure 3.7, and the time complexity of the remove operator is order of m square. So, where m is the length of the x, note that length of the solution decreases. So, the operator cannot be used for the problems with upper bound equal to lower bound. So, we have to remove x technique, you have to use it, x best to x I range from 0 to m, and x new is x, and A is designed as xi, and check it out, Fa less than or equal to L into Ba, continue it or remove the node from x new at the position I. Therefore, g of x new is less than g of x best, therefore, x best equal to x new. So, return x best. So, this is a way we have to use the remove operator pseudo code. Now, we have to move. Move is an operator that attempts to move all possible solution substring x suffix sub of the length n to all possible location j and perform the most improving move. So, if no move improves the fitness g of x best, the original solution is returned. Pseudo code is shown in the algorithm. On line 4 to 6, a substring x sub is selected from x and x new is created that is identical to x except for x sub which is missing. On line 7 to 9, x sub is inserted to all possible destination location j. An example, move operation where I equal to 3 and j equal to 1 is illustrated in the figure. So, the time complexity of the move operator is order of m minus n whole cube, where m is the current solution length and n is the length of the substring. So, the proposed solver also offers a second version of the move operator, that is called it as a reverse move. So, which is not only move the substring, but also revert it. So, function move of x comma n, where x best is x for I in range from 0 to m minus n, x reduce is x subtracting of x at position I with the length n, and remove x sub from x reduced for j in the range from 0 to m minus n. So, x new is x reduced, insert x sub into x new at position j if g of x new is less than g of x best. Therefore, x best to x new return to x best. So, move operator is a pseudo code. So, move from what 2 on line 7 to 9, like that we have to do that. So, this may do with the reverse move, and move operator not only moves the substring, but also it revert to it. So, here the operation where I equal to 3 and j equal to 1. Next, move all. Move all operator moves all occurrence of some node A up to some maximal distance d and chooses the most improving solution x best. Pseudocode is shown in the algorithm 3.4. Position P of all the occurrence of A in X are found on line 4. Then on line 5 to 9, for every distance I in the range from minus d to 2d except 0, the function removes the node A from the position P and insert it back at the position P plus I. An example, move all operation where A equal to 3 and I equal to 2 is illustrated in the figure 3.9. This complexity of the move all operator is order of cardinality of A d into Fm, where modulus of A is the number of nodes, M is the length of the X, F is the frequency of the mode A. F is the frequency of node A. So, this is the picture where move all operator pseudocode. So, function move all x comma d and x best, x is x best for node A in A position, find all position of a node A in X for I in minus d to d, where x is x nu. For P in POS, remove node A from x nu at position P, insert node A into x nu at position P plus I. If g of x nu is less than g of x best, then x nu equal to x best. So, return x best and move all nodes 3 by 2. So, this is the picture from 3 to 2. Therefore, note 3 to 3 by 2. Next, swap. Swap operator takes two argument n and p. It tries swap all possible substring x suffix sub 1 and x suffix sub 2 of length p and q in all possible locations I and j of x. After iterating through all possibilities, it returns the most improving solution x best pseudocode is shown in the algorithm 3.5. On lines 5 to 6, the algorithm checks that the selected substring in position I and j are not overlapping. On line 8 to 9, the two substrings are selected, and on line 10 to 13, the swap is performed by removing and then reinserting both the substrings into former location of the other substring. So, an example, swap operation where p equal to 2 and q equal to 1, I equal to 3 and j equal to 1 is illustrated in the figure 3.10. So, the time complexity of the swap operator is order of m into m minus p into m minus q, where m is the length of x and p and q are the length of the substrings x substring 1 and x substring 2 respectively. The proposed solver also offers a second version of the swap operator, that is called as reverse swap. So, which is not swaps the two substring, but also revert them. So, this is the inbuilt function of the swap operator pseudocode. Function swap of x comma p comma q, and x is x best, and then for I varies from 0 to m minus p, and then where j range from 0 to m minus q. If I is greater equal to j and I is less than j plus q, or j is greater equal to I and j is less than I plus p, and continue, and x is x nu. Therefore, we have a sub 1 of a substring x at the position I with length p, and x sub 2 is a substring x subject to the 2 of a substring of length x at the position j with length q, and then remove once again x sub 2 maps to substring of x at position j with the length q, and remove x sub 1 from x nu at position I, insert x sub 2 into x nu at position I, remove x sub 2 from x nu at position j, insert x sub into x new at position j if g of x new less than g of x best. Therefore, x best maps to x new and return x best. So, the algorithm is swap operator pseudocode and swapping of second and second, that is blue color first swap to second 4 to 3 and 3 to 4 and then 5 to 2, 2 to 5. So, it will come 1, 5, 4, 2, 3, 6. So, the swapping operator where p equal to 2 and q equal to 1 and I equal to 3 and j equal to 1. So, this apply it so that it will be swap. Next, exchange node. Exchange node operator iterates over all possible node pairs a comma b and exchanges all occurrence of these nodes in X. After iterating through all possibilities, it returns the best solution X best. So, the key part of the algorithm is on the line 10 where it iterates over the elements of X and swaps any node A from node B and vice versa. So, an example, exchange node operation where A equal to 3 and B equal to 5 is illustrated in the figure 3.11. So, the time complexity of exchange node operates order of cardinality of A square m, where m is the length of x and modulus of A is a number of nodes. Note that the value of f suffix A and f suffix B also swap. So, this is the corresponding algorithm of a pseudocode, and then the figure 3.11 is a exchange of a node operator. Next, exchange first n nodes. Exchange first n nodes operate the generalization of exchange node operator. The main difference is that this operator also iterates over allowed number of exchanges n. Each iteration makes only exchange of first n occurrence of nodes A and B, leaving the other occurrences at their original position. Pseudocode is shown in the algorithm. On line 7, the counters CA and CB are initialized. On line 11 and 14, the relevant counter are incremented. If A is exchanged from B or B is exchanged for A, the condition on lines 9 and 12 are extended by the condition that the relevant counter does not exceed the value of n. Example, exchange first n nodes operation where A equal to 5 and B equal to 3 and n equal to 2. We illustrated the example. The generalization comes at the price of the increasing time complexity. The time complexity of the exchange first n nodes is operator of order of cardinality of A square mf, where m is the length of x, cardinality of A is the number of nodes and f is the biggest element of f. Note that f may change if the frequency of fa is greater than fb. So, this is the pseudocode as well as the picture of exchanging, and the number A equal to 5 and B equal to 3 and n equal to 2, and we can swap for all. For all swap, they do this pseudocode technique. Next, two optimization. Two-opt operators tries to reverse all the possible substrings x suffix sub of the original solution x. If one of the reverses result in improved fitness g of x new, the function returns a new solution x new. Otherwise, it returns the original solution. Pseudocode is shown in the algorithm. On line 3 to 4, the boundaries I and j of the substring x sub are selected, and then on line 6, the substring is reversed. An example, two-opt operation where I equal to 1 and j equal to 4 is illustrated in the figure 3.13. The time complexity of the two-opt operator is order of m cube, where m is the length of the x. So, this is the two-opt operator example where I equal to 1 and j equal to 4, and C two operator at a time we have to do with 2 to 5 and 3 to 4. that will be swap like this, and the complexity is order of m cube. Next, perturbations. Perturbation are very similar to the operators because every perturbation is associated with some neighborhood, but instead of exploring the neighborhood exhaustively, the perturbation return a random solution from the given neighborhood. All the perturbation also accept a parameter k, which is used to parameterize the perturbations strength. A larger parameter k corresponding to a larger neighborhood from which a solution is chosen. This section describes the 6 perturbations that are implemented in the proposed solver, namely double bridge, reinsert, random swap, random move and random move all. So, these are all the implementation we have to do. Next, double bridge. Double bridge perturbation split the original solution x into k substrings and revert them. Pseudocode shown in the algorithm. On line 2 to 4, the algorithm generate k random indices plus the first and the last index of x and stores the indices in a shorter array I. Then on line 5 to 6, the function reverses the k plus 1 substrings bounded by the indices. An example, double bridge perturbation where k equal to 2 and I equal to 2, 5 is illustrated in the figure. So, the proposed solver also offers a second version of double bridge called random reverse double bridge, which randomly reverses only some of the substrings with the probability p equal to 0.5. So, this is the pseudocode where a function double bridge x comma k where generate a set of k random indices and I equal to I plus 0 comma m minus 1. Sorting I is in ascending order for I equal to I in cardinality of I reverse x between the position II and I suffix I plus 1. So, this is the double bridge perturbation, this is the double bridge C, double bridge perturbation and corresponding the the pseudocode is above and the picture representation 17 and 257 and 6389 separate parallelly you have to do and it is called as a double bridge. So, k equal to 2 and I equal to 2 comma 5 at a time you have to do that. Next, reinsert. Reinsert is a randomly select k nodes, deletes all of their occurrences in x and then reinsert them at random location. Pseudocode is shown in the algorithm 3.10. First k nodes are randomly selected on line 2, then between the line 4 and 8, the algorithm iterates over selection of nodes A in I and B in x. If A equal to B, the node B is removed from x and the counter C is incremented. Finally, on lines 9 to 10, the algorithm insert the node at a random position of x for every previously removed node. An example, the reinsert perturbation where k equal to 1 and I equal to 3 is illustrated. So, function insert x comma k, I generate k random nodes from A for node A in I and start with C equal to 0 for node B in x if A equal to B and C to C plus 1, remove node B from x, I in the range from 0 to C, insert node A into x at random position, return x. So, we remove the 3 here and then reinsert to 3 here like 1 to 3, 7 to 4 like that and finally we can do that. So, if we use this pseudocode, we can easily do the process of reinsert. So, reinsert perturbation example k equal to 1 and I equal to 3. Next, random swap. Random swap perturbation select 2 nodes from x and swap them. So, this is repeated k times. Pseudocode is shown in the algorithm 3.11. An example, random swap perturbation where k equal to 2 is illustrated in the figure 3.16. The first iteration swaps the nodes at the position I equal to 1 and j equal to 5, and the second iteration swap the nodes at the position I equal to 3 and j equal to 6. Note that the swap operator is used during the local search. Perturbation k should be larger than 1. So, this should be prevent the solver from reverting the perturbation step by single call of the swap operator. So, this is the pseudocode. This is the picture corresponding how the swapping occurred where k equal to 2. Next, random move. Random move perturbation is a randomly select k nodes from x and moves them to random location. Pseudocode is shown in the algorithm 3.12. An example, random move perturbation where k equal to 2 is illustrated in the figure 3.17. The first iteration, node 7 at the position I equal to 1 is moved to j equal to 4, and in the second position, node 8 is moved to j equal to 2. And note that if the move operator is used during the local search, parameter k should be larger than 1. So, this should be prevent the solver from reverting the perturbation step by a single call of the move operator. Next, random move all. So, random move all is similar to the move all operator, but it moves every node by a different distance. It moves all occurrence of a node A up to the some maximal distance k. Pseudocode is shown in the algorithm 3.13. On line 4, a random node A is selected and all occurrence of A is x is found. Then on line 5 to 8, every occurrence of A is removed from x and moved by the random distance. An example, a random move for all perturbation where k equal to 1 is illustrated in the figure. This example, the distance distinct sequential takes the following values -1, 0, 1. So, this is the pseudocode generated, random move for all perturbation and random move all 5 by 1. So, I equal to 2, 5 where k equal to 2 is picturized. Next, construction strategies. The construction strategies generate an initial solution that is used later as a starting point in all the meta heuristics. So, this section describes the 3 construction strategies implemented in the proposed solver. They are a greedy random and a random replicate. All of them are guaranteed to return a valid solution. So, a valid solution is a solution that is necessarily feasible with respect to optimized problem definition, but it satisfies the lower and upper bounds. Next, greedy. Greedy construction strategy repeatedly calls the insert operator until a valid solution is created. If the user wants to use the greedy construction strategy, it is necessary to deal with the invalid solution in the fitness function g. This means that the fitness g of x should decrease if the frequency f suffix nu of the new solution x suffix nu are the closer to lower bound or upper bound than the frequency f of the solution x. So, this can be expressed as h of f comma lb comma ub equal to lb minus f for f is less than lb, 0 for lb less than or equal to f less than ub, and f minus ub for f is greater than ub. So, this is the function we can define for h. So, this is called as a greedy construction. So, the g of x nu is less than g of x if f into summation I equal to 1 to n h of fi nu comma lbi comma ubi is less than summation I equal to 1 to n h of fi comma lower bound and upper bound. Next, random. This is the most straightforward construction strategy of the 3. It inserts nodes one by one to random locations until at lower bounds are satisfied. So, return solution always has f equal to lb. So, the problem has lower bound not equal to upper bound. It is recommended to use the insert and remove operators. Later during the local search, the random construction strategy addresses problems where greedy construction is not efficient in terms of the trade off between computation time and fitness improvement per iteration. Next, random replicate. This construction strategy generates a random permutation of all nodes, and then it repeatedly appends its copies to the initial solution until all lower bounds are satisfied. If one of the node frequencies reaches the upper bound before all other nodes reach the lower bound, it is not included in the replica. So, the result of this construction strategy is always valid solution. So, the random replicate strategy is proposed in this talk to address the problems represented as several perturbations that are similar to each other. So, non-perturbation flow shop is an example of such a problem. Next, local search strategies. Local search strategies are a function that choose the order in which the operators are invoked, and after reaching a local optimum, they return the acquired solution. All the implemented local search strategies are a variation of the variable neighborhood descent. So, this section describes the 5 local search strategies implemented in the proposed solver. One is the basis VND, pipe VND, cycle VND, random VND and random pipe VND. The VND mean variable neighborhood descent, and then pipe VND, all the algorithm except a list of available operators O. Next, basic variable neighborhood descent. So, a basic variable neighborhood descent iterates through the list of O sequentially, that is order. So, the fitness does not improve after the selected operator OI. So, it selects the following operator O suffix I plus 1 and tries again. If the fitness G of x improves after the call of the selected operator OI, it returns to the first operator O1 in the list. Once it reaches the end of the list without any improvement, it returns the solution x. So, the pseudo code is shown in the algorithm. So, this is the basic variable neighborhood descent pseudo code. So, function basic variable neighborhood and do x previous to x for O in 0 in O and x new the O of x, and g of x new is less than g of x and x new is x, and break so that g of x less than g of x previous, then return x. So, this is the algorithm of pseudocode of the BVND, that is basic variable neighborhood descent. Next, pipe variable neighborhood descent, that is PVND iterates through the list O sequentially as well, also same as BVND. If the fitness G of x does not improve after the selected operator OI, right, OI, it selects the following operator O suffix I plus 1 and tries again. So, the main difference is that the fitness G of x improves after the call of the selected operator OI. The algorithm calls the same operator repeatedly as long as the operator improves the solution x. So, if PVND reaches the end of the list without any improvement, it returns the solution x. So, the pseudocode is shown in the algorithm. Note that the operation list O can be large, and therefore, on line 6 to 7, the algorithm checks whether it reached the last improving operator. If that is the case, it stops so that it does not have to go through the rest of the list. So, this is called as pipe variable neighborhood descent pseudocode. Next, cycle variable neighborhood descent, CVND also iterates through the O sequentially. So, the difference between PVND and CVND is that regardless of whether the fitness G of x improves or not after the call of the selected operator OI. So, the CVND moves to another operator OI plus 1. So, the CVND remembers the last improving operator O lost, and if O suffix I plus 1 equal to O lost, it stops and return the solution of x. So, the pseudocode of this algorithm, note that on line 6, 7, the algorithm checks whether it reached the last improving operator, and if that is the case, it stops. So, does not have to go through the rest of the list O. So, this is called as CVND, cyclic variable neighborhood doesn't pseudocode.